Welcome back. We're continuing our journey in chapter 5 here, and here's an introduction to a definite integral. And these are definitely very, very useful. A definite integral looks like this. We would say that this is an integral of f of x from a to b dx. Now, our dx comes from our delta x, and we're going to make that connection here in just a moment. So it's called a definite integral because we have boundaries a to b. So x is clearly going from a to b. And the connection that we're going to make from the lesson from 5.1 is that the definite integral is comes from a Riemann sum, which we are decent at this point. So function f is defined from a to b, is integrable on a to b if the limit as n goes to infinity of this exists. In fact, we're going to make a big reveal now. This is the limit as n approaches infinity, summation k equals 1 to n of x, f of x. We're using the bar notation here. That's just any value between two node points, delta x. So whenever we have this, we can just jump to here. Now, we don't know how to do this quite yet. We know how to do antiderivatives. We've done those before, but bounded like this and plugging it in, we will need the next chapter, which is the fundamental theorem of calculus. That's where everything sort of changes for us in a good way. Makes it a lot easier to deal with. All right, and once again, we're dealing with rectangles, and so this is our base, our height, pardon me. And this is our base. All right, that's down here, delta x. This is a delta x. All right, so what we're going to do for our first example is we are going to convert our Riemann sum that we're shoving n off to infinity, meaning the distance, the delta x is going to 0, basically, is what we're trying to do as n goes to infinity, because then we're line, and they're super close together. And that's the whole idea, is that we're ideally going to get small enough rectangles that we're going to get exactly the area under the curve. So we're going to find, this is a limit of the Riemann sum for f from 1 to 3. And they'll need to give us the boundaries for the problem. Unless it's a word problem, then we'll have to come up with the boundaries. And just a quick little insight to things that are coming. If you remember in trigonometry, when you would have like sine of theta equals 1/2, and you'd have to get the 1 in quadrant 1 and in quadrant 2, well, those can be boundaries as well. So that could be the a and the b. That's coming. So we're going to express it as a definite integral. So using our definition up here, this is going to be the integral from 1 to 3 of f of x. And I'm going to identify this as 3x squared plus 2x plus 1 dx. And basically what that's saying is we're taking our curve. This is our f of x. And we're finding the area from 1 to 3. Now, this is the exact area when we do the integral, because we're having n go off to infinity. All right. Let's find some areas under the curves, but these are very specialized functions. So we have a line here, y equals mx plus b. The slope is 2. The y-intercept is 3. And I want to draw this picture. So here's 3 up 2 over 1. So we're going to have a line that looks like this. And yeah. So let's get our line. And we are integrating from 2 to 4. So here is 2 and here is 4. Now I need the associated y values with this. So when x equals 2, 2 times 2 is 4, 4 plus 3 is 7. So that's making it up here. Obviously, my picture's not drawn to scale. This is 7. And this one here, when I plug in 4, 4 times 2 is 8, 8 plus 3 is 11. And what I'm looking for is this area right here. Now, this shape is called a trapezoid. And the area of a trapezoid is h over 2 b sub 1 plus b sub 2. Now let's orientate this. Our two bases are here and here, and our height is this distance here. So this is h, this is b1, and this is b2. So let's plug in what we have. H is 2. Do you see the distance from 2 to 4 is 2? B1 is the height here, that's 7. B2 is the height here, that's 11. Which gives us 18. Number 2, we have another straight line, but we're going to have some different characteristics with this one. This one has a y-intercept of -6. And it's going to cross at 3. And we are integrating from 1 to 6. So let's draw our line. And because we're integrating from 1 to 6, we're going to run into an interesting phenomenon here. Down here is negative area. It's below the y-axis, the x-axis. And up here is going to be positive area. And let's see where we are here. When x is 6, 6 times 2 is 12, 12 times 2 is 6 again. So we're getting 6 back. And down here, when x equals 1, that's going to be 2 times 1, which is 2. 2 minus 6 is -4. So this is a -4 down here. All right, so let's start with the green. Let's start with the red. Why not? So we'll start with the negative. Now that's a triangle. Distance from here to here is 2. So this is going to be area of the negative is going to be 1/2 the base times the height. That's going to be 2 times -4, which is -4. And the green area that's above the x-axis is going to be positive. That's going to be 1/2 times the base. This here is 3. And the height is 6. So that looks like it's going to be 9 to me, which means the overall area is going to be 9 minus 4, or 5. Now, number 3, I need a little bit more of an explanation for us. So I'm going to grab a blank piece of paper here. There we are. And I'm going to copy this one down. So this is our function in this case is y equals the square root of 1 minus x minus 3 squared. Now I just want to focus on that for a minute. And I'm going to resettle this, and I'm going to square both sides. And I'm going to add that to the other side. This is a circle with a center at the point 3, 0, and a radius of 1. So what's going to happen, and I want to point out this is positive here. You see it's positive there? Because if I work backwards and take the square root of both sides, I would get plus or minus. So what this is going to look like for us is the top half of the circle, because it's the positive half. And they only want us to go from 3 to 4. So the area of interest is only from here to here. So what that's going to tell us is we can just find the area of a circle divided by 4. It's only a fourth of a circle with a radius of 1. So this is going to be the area is going to be pi r squared divided by 4 for us. R is 1 in this case. So this is just going to be pi over 4. So this is all well and good when we can draw the picture, and it's a shape that we can that we know the formula for the area, like a trapezoid, a triangle, or circle, as we're looking at that. We're not always going to have the luxury of that. In fact, most of the time we won't, which is exactly where where the rest of the chapters is headed. So let's move on to the second page here. All right, so as I mentioned, when we're below the x-axis, it's negative area, and when it's above the x-axis, it's positive area. And so we have this graph here, and the area from A to B is 12, B to C is 10, and C to D is 8. And so let's see what we get as we go from A to B. This area will exactly equal 12. From B to C is going to be negative 10. Now from A to C, that's going to be 12 minus 10, which is 2. And from B to D, this is going to be negative 10 plus 8, which is a negative 2. Nothing wrong with negative energy. Area, pardon me. If we apply this to physics or something, the negative would indicate a direction, most likely. All right, we have a few properties of definite integrals. First off, the integral from A to A of f of x dx is 0. So when the boundaries are the same, there is no area. The integral from A to B of f of x dx is the same as negative integral from B to A, f of x dx. So when you switch the boundaries, you get an extra negative in there. And for the third one, the integral from A to B of f of x plus or minus g of x dx can be split up. And we do all the time. We often split them up. What this does for us very nicely is it makes it so that we can break it into a bunch of smaller, easier pieces, hopefully easier. The fourth one is the integral of from A to B of a constant times f of x dx becomes the constant times the integral from A to B f of x dx. And you've seen me demonstrate that in the past as well. And for the last one, I need a picture. So if we have some sort of function And we're going from A to B, B, and we have so we're going from here to here, looking for the area, and we have a point C somewhere in between. Then what I can do is I can take the integral from A to B, f of x dx, and I can split that up, the integral from A to C, f of x dx, plus the integral from C to B of f of x dx. Now you might be asking yourself, why would I even think of doing something like that? There's going to be times when that's going to be really convenient for us. So maybe the first chunk is negative, and we want to make sure that we're getting the positive version of it or something like that. We'll come back to these in another lesson, but let's do example 4, where we're going to full on do an integration of a curve, and we will need a few tools from the last lesson, section 5.1. So we are going to, basically what we're going to do is we're going to do the limit as n approaches infinity, the summation k equals 1 to n of x bar sub k cubed plus 1 delta x. Couple things to keep in mind. Now notice it's saying that's the right Riemann sum. So if you recall, delta x is equal to b minus a over n. And for the right Riemann sum, our x values were delta x times k. If you remember, the left one was k minus 1. All right, so let's go ahead and try to evaluate this. Let's actually go up here for a little more space. Limit and I'm going to go ahead and find my delta x. That's going to be 2 minus 0 over n. So that's going to be 2 over n. So what we have here is 2 over n times k. All right. Yes. So I'm going to take the summation of 2 over n k cubed plus 1, 2 over n. Yep, I missed the 1 there. 1. All right, I'm going to go ahead and pull the 2 over n out of the summation. This is going to become 8 over n cubed, k cubed plus 1. And if you remember, another piece that we're going to need is summation of k cubed was 1/2 n times n plus 1 squared. That was from the last lesson. And what I'm going to do is go ahead and separate these out. I'm going to pull that out of the summation. It doesn't need to be there. So that's going to be 16 over n to the 4th. Plus 2 over n summation k equals 1 to n of 1. All right, so I have 16 over n to the 4th. That becomes that. Plus, if you remember when you have a summation of a constant, it just becomes n. So this becomes 2 over n times n. Okay. That gets squared. So that becomes a 1/4. Limit. And this becomes 1/4. And then we have n squared plus n squared plus 2. The n's reduce out. Okay. So I'm going to notice if I FOIL this out, which I'm not going to, do you notice that I'm going to get n to the 4th power? And when I have n to the 4th power over n to the 4th power, that means that whole, these go to 1, which means we're getting 16 over 4 times 1 plus 2. Now that may seem a little overwhelming, and understandably. You have to take some time and really break this down into each little component. You may need to review the previous video as well. I hope that helped.